let's say you want to send a message to your friend. You want to tell them, hey, I think you're cool. How could you do it? You could send them a text message. You could call them. You could go out to their bedroom window and throw rocks at their window until they open it. You could yell at them across the street. You could send them an email. You could fax them. You could put a message in a bottle. You could get one of those toast printers that prints on toast, and you could send them a message that way. Or you could somehow combine all of these messages together and do them at the same time.
You should have sent me a woof.
A what?
When you send a woof, it goes to your home phone, cell phone, email, Facebook, Twitter, and home screen, all at the same time.
Woof.
Woof.com.
But they would all communicate more or less the same thing. In chemistry, there are different ways that you can communicate an enthalpy change. They all have the same general meaning, but there are different pros and cons to the different types. And so that's what this lesson is going to be about. So the 4 ways that we can communicate these changes are, first of all, we can state the molar enthalpy of a specific reactant in a reaction. We can state the enthalpy for a balanced chemical equation. We can include an energy term in a balanced chemical equation, or we can draw a potential energy diagram. And I'll show you the same example with all 4 of these methods so that you can get a sense of similarities and differences. So the example that we're going to look at is the formation of methanol. So if we want to make methanol, let's remember first what it is. So methanol, it's an alcohol. It's got 1 carbon, right? Because it's a meth. So it will be CH3OH. And methanol is going to be a liquid at room temperature. And if this is a formation reaction, then we're forming this guy from his elements. So we're forming it from carbon, which in its elemental state is a solid, and hydrogen, which comes as a diatomic gas, and oxygen, which also comes as a diatomic gas. And if we're going to balance this chemical equation, we've got 1 carbon, 1 carbon, got 4 hydrogens over here, 2 times 2 is 4. We've got 1 oxygen over here, we've got 2 over here. Now, we would normally double, right? We would double my oxygens on this side. That means that I've now got 8 hydrogens, so I need 2 times 4. It's 8. I've now got 2 carbons, and I can balance this oxygen with a 1, right? So I've got 2 oxygen atoms on the left and 2 oxygen atoms on the right. So let's look at our first method. Method 1 is by writing a molar enthalpy for a reaction. Molar enthalpies are determined empirically, experimentally, usually through calorimetry. And if I'm wanting to use this method, I have to specify what substance I'm talking about, and I have to specify the type of reaction that's happening. So let's look at my example. We've got the formation of methanol. Now remember, when we're expressing these enthalpies, we can use a little subscript letter here to specify the reaction type. And the F means that this is a formation. So that's my reaction type. And that's a really important piece of information. It's easy to miss that little F, but it's very important because if I'm forming methanol, that's the reaction we specified above, right? I'm building a methanol molecule from its elements. That's very, very different from burning methanol, right? Here's the same substance. I've got methanol down here, but the only difference on the left side of this is that this is a combustion. The reaction type here is specified by this little subscript. The second piece of information that we're getting in here is the chemical species. So it's usually listed underneath. Here's my chemical formula for methanol. So that's telling me what species or what chemical entity I have here. So this is the formation of methanol. And as you might expect, if I'm forming a different molecule, if I'm forming butane or glucose or some other molecule, it's going to have a different enthalpy because it's a different reaction. So I have to pay attention to those 2 things, my subscript here and my chemical species. Then once I do that, notice that this is a molar enthalpy. the subscript M tells me this is a molar enthalpy, and I can see that in my unit. This is energy per mole, kilojoules per mole of whichever species this is. So this is kilojoules per mole of methanol that are formed. And my naught here means that this is at standard conditions. And I'll put a little link to what that means in case you don't understand. So what this notation is specifying is that this reaction has taken place. I formed 1 mole of methanol. And you might notice something new here, which is I have a coefficient that's a freaking fraction. We need to pause here for a minute. So sidebar, we need a little gavel noise. We need to take a sidebar here. And we need to go back to basic chemical balancing. When you learned how to balance in your introduction to chemistry, if you were smarty pants, you might have said, well, this would be a lot easier if I can just put in a fraction. You get to some of those weird ones where you've got an odd number of oxygens on one side and an even number on the other side. You said, well, if I could just put in a coefficient of a half for my oxygen, then that's going to make it a lot easier. And your teacher probably told you, we're not going to do that yet. Balance your chemical reaction with lowest whole number coefficients. Well, now we're going to let you use fractions. The reaction that we specified before, we said we want to form 1 mole of methanol. But if we balance the equation like we did in the example, we end up with 2 moles of methanol being formed. That's the only way to get whole number coefficients. So if I want to show the reaction for 1 mole of methanol, I have to divide everything by 2. I have to make this into a 1, right? So if I divide this by 2, this is an automatic 1, divide this by 2, divide this by 2, divide this by 2, and then I simplify, that's going to give me this balancing down here where I've got 1, 2, 1/2, and 1. This gives me a coefficient of 1 for my methanol, which is what I need, and I have a fraction for oxygen. And so that's now okay. You're allowed to use fractional coefficients in chemistry from this point forward, and in some cases, like in this case, you're going to need to. Okay, so let's come back to our problem. So we have the formation of 1 mole of methanol. If we have this bottom example here where we're burning methanol, so this is an enthalpy of combustion, then we're assuming that we have this combustion reaction that's taking place. And in order to balance it with a coefficient of 1 for my methanol, we need 3/2 as my coefficient for oxygen. So again, I've got a fractional coefficient. That's okay. Now remember too, when we're expressing enthalpies, we have a sign convention. These are both negative enthalpies, and that's giving me some really important information. So when I have a negative enthalpy, that means that my reaction is exothermic. So both of these reactions are exothermic reactions because they have a negative enthalpy or negative molar enthalpy. And if I had a positive enthalpy, then that would mean that my reaction was endothermic. I'll put a little link that'll appear that will bring you back to the lesson where we talked about why these come out as positive and negative. But that's information you'll need to be able to pick out. Method 2, enthalpy changes with a reaction. In this method, we're going to have a balanced chemical equation, and then the enthalpy change is going to be written next to it. Let's notice a couple things. So first of all, I'm starting with my same reaction that I had before. So I'm forming methanol. Here's my enthalpy, negative 239.2 kilojoules. So this is the enthalpy for this reaction as written. I can just put an R because the R is telling me I have some reaction that's specified, and the reaction is specified by the equation over here. Now notice that my units here are not kilojoules per mole because this isn't a molar enthalpy anymore. This is an enthalpy for the reaction as written. Now this would be the enthalpy change for every mole of methanol that's produced, or for every mole of carbon that's consumed because they have coefficients of 1. But this is also the enthalpy change for every time 2 moles of hydrogen react, or every time half a mole of oxygen react. So we'll look at how we can convert this into a molar enthalpy, and that has to do with just dividing by however many moles of the thing that I'm specifying. And the enthalpy here depends on the balancing that I have. Because if, for example, I had balanced this reaction with lowest whole number coefficients like this, then notice my coefficients are double what they were in the top reaction. Well then, what do you think would happen to the enthalpy for the reaction as specified? And if you said that it doubled, you're correct. So the enthalpy here would be negative 478. So the enthalpy here would be negative 478.4 kilojoules. And you notice again, it's not a molar enthalpy, it's an enthalpy for the reaction as written. If I found the molar enthalpy for methanol, for the formation of methanol in either case, I'm going to get the same value. Because in my top reaction, this was the number of kilojoules per 1 mole. In my bottom reaction, this was the number of kilojoules per 2 moles. So if I want to know the number of kilojoules per 1 mole, I would divide this by 2, and I'd get back to this number. So if I want to turn something from a molar enthalpy into an enthalpy written as next to the reaction, how can I do it? Natural gas wells sometimes are sour, which means that they contain hydrogen sulfide. Hydrogen sulfide is a really, really nasty, toxic compound. And you can eliminate hydrogen sulfide by burning it, by flaring it off. So if you burn the hydrogen sulfide, you turn it into sulfur dioxide, which is not toxic. And when you do so, it burns, it combusts according to the reaction that's specified here. And we're telling you that the standard molar enthalpy of combustion of hydrogen sulfide is negative 518 kilojoules per mole. So if we want to express that as a standard enthalpy change for the following reaction equation, how can we do that? Well, let's first identify what's the chemical that this is a molar enthalpy for. This is a molar enthalpy per mole of hydrogen sulfide. So for every mole of hydrogen sulfide I combust, I get 518 kilojoules of energy. Now here, I'm combusting 2 moles of hydrogen sulfide. So we could figure out the standard enthalpy here 2 ways. One way would be just to use unit analysis. So I could say, okay, I know I've got negative 518 kilojoules per mole of H2S. That's how much energy is going to be released. In this reaction as written, there are 2 moles of H2S that are going to be burned. And so that means that this value is going to double, right? 518 times 2, which will give me 1,036 kilojoules. It's still negative, right? It's still exothermic. And so that would be my enthalpy for the reaction as written. 1,036 kilojoules. Notice that it's not a molar enthalpy, right? A really common mistake would be to shove a per mole in there, but it's not a molar enthalpy. It's for this reaction as written here. Method 3, as a term within a balanced chemical equation. So in this method, it's similar to the last one, where we're going to have an enthalpy change for a reaction as written. So it's not going to be a molar enthalpy, but instead of writing it outside the equation as its own separate kind of thing, right? Delta H of the reaction equals whatever. We're going to include it in the reaction as a term. So how does that work? Let's remember, first of all, that if I have an exothermic reaction, that means that we're producing energy. So if we're producing energy, energy is being given off, and it'll be on the product side. If I have an endothermic reaction, the reaction is requiring energy, so that means that energy needs to go into it. The energy term needs to be on the reactant side. And just in case you've forgotten, well, how do I know if it's going to be an exothermic or endothermic reaction? You can look at the sign of the enthalpy term. So if you're given a molar enthalpy, or if you're given enthalpy as a term, so if you're given the enthalpy written outside of the reaction, or you're given the molar enthalpy, you can look at the sign of it. So if the enthalpy is negative, that means that it's an exothermic reaction. If the enthalpy is positive, that means that it's an endothermic reaction. And that's how you can tell which side it's going to go on. So for the reaction that we've seen before, my formation of methanol, what's it going to look like? Well, I remember that the enthalpy was negative 239.2 kilojoules for the reaction as we wrote it for 1 mole of methanol. So I've got a negative sign. That means that it's exothermic, so the energy has got to be on the product side. So the energy is going to be produced, and it doesn't produce negative 239.2. The sign doesn't have meaning here. We can't produce negative energy. We're producing 239.2 kilojoules of energy. And just like with the last example, if this is balanced differently, if we had a coefficient of 2 here, well then this value would have needed to have doubled, right? Because instead of producing 1 mole of methanol and this much energy, we would produce 2 moles of methanol and twice that amount of energy for 78.4 kilojoules. If you have an endothermic reaction, then the energy is going to be listed on the left side, right, on the reactant side. And you'll never add a negative amount of energy. So if we have a reaction like this and we want to turn it from this style, where we have the enthalpy, this is our method 2, enthalpy for a reaction is written. We want to add it as a term. How do we do it? Well, the most important information here is the sign. We've got positive enthalpy. That means that it's endothermic. So that means the energy term has to go on the reactant side. So when we rewrite this, I have my ethane. It's going to require 136.4 kilojoules of energy. And when you do that, you get 1 mole of ethene and you get hydrogen. Finally, method 4. In method 4, we're going to express the whole reaction as a potential energy diagram. And that's going to let us visually see the relative enthalpies of the reactants and the products and the energy that's being gained or given off. These styles will be helpful if we're considering reaction in terms of calorimetry. So if we're doing a calorimetry experiment like you've done, and the potential energy diagram then just shows how much potential energy the reactants and the products have. So this is an endothermic reaction because the reactants have got less potential energy than the products. So because of that, there's an increase in potential energy, and that's why the sign of the enthalpy term is going to be positive. And what we're going to do when we create our own is we're not going to write the word reactants and products. We're going to write in the actual chemical species that are reacting. So let's take our example reaction again. We've got the formation of methanol here. It's the reaction that we've seen now. This is the 4th time. We're going to represent it as a potential energy diagram. So potential energy diagrams are always set up with potential energy on the y-axis and the reaction progress. Sometimes we call it the reaction coordinate on the x-axis. And you notice there's not a time scale because we don't really care, in this instance anyways, about the time frame that this reaction occurs in. We just care that at 0, we have the reaction that hasn't started yet, and by the time we get to the end of the graph, the reaction is complete. And the potential energy too, we don't typically worry about a scale. We just sketch the reaction, and we're going to label the numbers. We're going to label the change, which is the only thing that we really care about. So what information do I have to pick out in order to build this? Again, is my sign. This is a negative enthalpy, which means that it's an exothermic reaction. So for an exothermic reaction, that means that my reactants had more potential energy than my products. So my reactants are going to have a higher level on the graph, a higher amount of potential energy than my products will. And let's make this a little longer because I've got 3 things that I need to write up there. And then my product is my methanol over here. So we're going to write in this with its balancing. My reactants were carbon, solid, and 2 hydrogen gases, and 1/2 oxygen. Those are my reactants. My product was 1 mole of methanol, CH3OH, liquid. And then the enthalpy for this reaction here as written was negative 239.2 kilojoules. Again, notice the units are just kilojoules, not kilojoules per mole. Let's try another example of that. If I want to communicate this reaction as a potential energy diagram, the decomposition of water by electrical energy from a solar cell. We don't really care about any of that stuff, but we do care that this is the decomposition of water, because I'm going to need to know what my actual reaction is. I'll put a link to how to predict reactions in case you forget how to do that, but the decomposition of water will be this reaction here. So I'm starting with liquid water, it's decomposing, so it's producing oxygen and hydrogen. Those would both be gases. And I'm being given the molar enthalpy for this reaction. So I want to balance this where my water maintains its coefficient of 1. So that means that instead of doubling this to get 2 oxygens over here, I'm going to half my oxygens on the right to get 1 oxygen over here, because a half times 2 is 1, right? So I've got 1 oxygen over here, I've got 1 oxygen over here, then my hydrogens are balanced. Then when I put this onto my reaction coordinate, let's label my axes. I've got potential energy, and I've got my reaction progress on the x. This is an endothermic reaction because it's got a positive enthalpy. So that means that my reactants have got less potential energy. My water has got less potential energy than my products. They have more. My oxygen and my hydrogen. And the enthalpy change then for this reaction is positive 285.2 kilojoules. And if I had balanced this with a 2 and a 1 and a 2, which I could have, then this value would had to have doubled as well in order to account for that. So if you want to practice this, you can try writing the standard enthalpy changes for cellular respiration and for photosynthesis by using the 4 different methods that we did in the lesson. So here's the first one to try. 1 mole of glucose is consumed during cellular respiration to release 2,802.5 kilojoules of energy. And I'll put a link to the solution of this.